The common ion effect. So if a solution already contains, or you add some ions to it, that is also part of what you're assuming could work out to be a precipitate. Or if it's already dissolved in the solution, as a solute in that solution. And so if it is an ion that is in common with it, we have to figure it into our calculations. So for example, if we're trying to dissolve silver chloride into a solution that has sodium chloride in it, that chloride ion is in common between the solution already and the ion that we're trying to dissolve in there. So we have to factor that into our calculation. So we're going to do this using an ice table to help organize our data. So let's try it out. Given the KSP of a lead chromate, given the KSP of lead chromate is 2.3 times 10 to the negative 13, really insoluble, determine the molar solubility of lead chromate in a solution, so not just by itself going into water, but in a solution of 0.1 mole per liter sodium chromate. So the lead chromate's trying to dissolve into this solution, but there's already some sodium chromate in there. So this chromate ion is in common to it. So the fact that there's already some of this ion in there means that the lead chromate is going to have trouble dissolving, because if you imagine your dissociation equation for your lead chromate trying to dissolve, you get your lead ions and your chromate ions. But if the concentration of chromate is something higher than 0, it's going to be pushing back on the left-hand side of this, or wanting not as many ions to dissolve. So the lead chromate's trying to dissolve. The fact that there's already some chromate ions in their common ion is going to minimize the amount that can actually dissolve. They have the shift to the right. So let's build our ice table. For the precipitate, or the solid that we're talking about, we're going to use variables where we don't know what the concentration is going to be. We're going to solve for x just like before using the equilibrium expression, in this case the solubility product constant expression. And we're going to, again, make sure we get an answer. We're not just solving for x, but we want to associate that with an answer. So here's our equation. And again, that really should be an equilibrium there that we're talking about. So we want to know, okay, how much of this is actually going to dissolve? Now, if this were something other than a solid or liquid, we would put in our values initially and with the changes in equilibrium. But since this is a solid, its concentration as a solid will not change. So we don't have to worry about that column. Given the question, we know that we're starting off with no lead in the water that we're trying to dissolve in, but that sodium chromate has already put in 0.1 moles per liter of just the chromate ion. So it's going to minimize the amount of lead chromate that can dissolve. So we're factoring that number in. So both of these are going to go up because it is a 1-to-1 ratio. So there's going to be, these are variable x. So this will be going up by x. And we're going to have our final value of x there. This is going to be going up by x as well. But we know based on the KSP, the shift to the right is going to be pretty small. It had a really small K value. So the shift from the reactants to the products is going to be quite small. So we should check this, but essentially what we could imagine is that if that KSP is really small, X is going to be quite small relative to the initial concentration of chromate. And so probably the final concentration of chromate is going to be pretty close to 0.1 anyways, so we can just use it as 0.1. We can use the 100 rule to check that if that's our line that we are drawing, and say, okay, if the concentration divided by the KSP is over 100, we can simplify. So therefore, we can set up our KSP expression with just 0.1 instead of being 0.1 minus x here, because we're saying, okay, well, x is going to be really small when compared to 0.1. Let's just ignore it. It's not going to make much of a difference. We solve for x, and we end up with our x value being 2.3 times 10 to the negative 12, which is our concentration of lead ions, which means, because it came from the lead chromate, that must be the amount of lead chromate that dissolved. So the amount of lead ions came from the lead chromate. So if the amount of lead ions that's in solution is 2.3 times 10 to the negative 12, the amount of lead chromate that dissolved must be 2.3 times 10 to the negative 12 moles per liter. And so the molar solubility of lead chromate is 2.3 times 10 to the negative 12 moles per liter.